In this video, we'll look at another test for the infinite series to see whether it is convergent or not. And the name of this test is called n-term divergence test. So for example, if you're given an infinite series a1 plus a2 plus a3 and so on, so you can use the summation notation to represent this. And the nth-term divergence test is actually quite easy to understand. You just have to take a limit of the individual term you have in the infinite series. In case the limit itself is non-zero, we can automatically claim that it is a divergent series. And divergent is in the sense that the series is actually going to infinity, which means, of course, automatically it is not convergent, right? Because convergent series means it must be approaching certain limit point. And let's look at some examples here. So please look at the current series that is given. And I think it is quite obvious that it cannot be a geometric series. For example, if you don't fully understand this problem, you can write the terms down one by one. So actually the series looks like you are having 5 over 3 in the first term, and then the next term is 9 over 8, right? And the next term is gonna be 13 over 13. So you can keep going like this. I think it's quite obvious. It is not geometric. You see, the fact is that if it is geometric, we don't have to learn a new method, right? We can just do it by the geometric series test, which is the topic in the previous video. So you can try to use the current test, which is called the n-term divergence test. You just have to take the limit of the term that we have. And this limit computation is actually quite simple, because for a rational function where you have a polynomial divided by polynomial, what you can do is that if you're taking a limit n goes to infinity, only the dominating term, which is the term having the highest degree, is important. So I just skip the remaining terms. So I can skip the constant terms here when n goes to infinity. So you see n is cancelled out, which means we have the number 4 over 5. And of course it is non-zero. And based on what we set up here for the m-term divergence test, so we understand that by the m-term test, our current problem is actually divergent. And let's try to take a good look of what's happening here in case you don't fully understand the test. You see? What is the meaning of this number 4 over 5? It means that when n is big, we expect that our term is actually close to 4 over 5. Very close. They are not the same. They are not the same. But our term itself is actually very close to 4 over 5. If n is actually big, if an is actually big, and it means that, and when n goes to infinity, we expect that each term look quite close to something like 4 over 5 plus 4 over 5 forever. So 4 over 5 numerically is the same as 0.8. So you can see what's happening. You keep adding 0.8 every time, and of course the sum keeps increasing every time without any limit, right? At the end, of course, it is going to infinity. And that's the reason why when the limit is non-zero, we expect that our series is actually divergent, but we'll add a note here. So I would like to emphasize that the other direction, where when the limit is 0 for each term in the infinite series, there's no conclusion we can draw based on the n-term test. So what does it mean for no conclusion? No conclusion means the series can be convergent, it can be divergent. We don't know the answer yet. We don't know the answer yet. If the limit of each term is 0, and it is actually quite easy to pick an example like this. But it is an important note, which means the m-term test only works for one direction, which is the fact that when the limit of each term is non-zero, we know it is divergent. But when the limit of the term is actually 0, we cannot say it is convergent. We don't know the answer yet.